Okay, so let's continue our discussion on the basics of acid-base disorders. Let's talk about metabolic acidosis. So, in case of metabolic acidosis, there's a fall in bicarb. Because the primary disorder is metabolic, the compensatory response is going to be respiratory. And because in the primary disorder, there was a fall in bicarb, so as a compensation, there's going to be a fall in PaCO2. Now, the predicted PaCO2 after this fall can be calculated using this formula, and this formula is commonly called Winter's formula. There are many other different formula that can be used, but this is the one that is most commonly used. Another thing to consider is the time frame. So the time frame in which this compensatory response will take place is going to be around 12 to 24 hours. Now, if the measured value of PaCO2 lies within the range of this predicted value of PaCO2, then that means there's a simple disorder present. But if the measured value of PaCO2 does not lie in this range of predicted value of PaCO2, that means there's something else is going on, right? So there's a mixed acid-base disorder. If the PaCO2 is above that range, that means that PaCO2 is higher than it should be if only compensation was present. Then it means that there's additional respiratory acidosis present. Why respiratory? Because the PaCO2 is higher, and we are not talking about bicarbonate here. And why acidosis? Because again, CO2 is acid and that's high. Similar is the case with respiratory alkalosis. So if PaCO2 is lesser than the range, then it's going to be respiratory alkalosis. Why respiratory? Because of PaCO2. Why alkalosis? Because CO2 is an acid, and if CO2 falls, then that's basically alkalosis. In case of metabolic alkalosis, the structure is pretty much going to be similar as we discussed about metabolic acidosis. The only difference is going to be that bicarb increases, as a result CO2 increases. We use a different formula for calculating the predicted PaCO2, and the time frame is slightly more than metabolic acidosis. Otherwise, this part pretty much remains the same, which means if the measured PaCO2 is within the predicted range, then that means it's a simple disorder. If not, then it's a mixed disorder. If PaCO2 is more than the range, then there's respiratory acidosis, and if less than range, then there's respiratory alkalosis. Now, this one concept that's probably good to understand. So the compensation for metabolic alkalosis is poor. Let's understand why this is. And for this, we need to understand the alveolar gas equation. By using the alveolar gas equation, we are basically calculating the partial pressure of oxygen in the alveolus. So if there is metabolic alkalosis, then there should be a compensatory increase in PaCO2, like we just discussed. And for this to happen, we need hypoventilation. So whenever there is hypoventilation, there's going to be hypoxia, right? And this hypoxia is going to be this hypoxia is going to be a drive for hyperventilation, and as a result, this hyperventilation is going to decrease PaCO2. And why do I say that? Because if alveolar O2 is going to decrease, then that means arterial PaO2 is also going to decrease, and this is what basically leads to hypoxia. So again, metabolic alkalosis, bicarb increases, as a result PaCO2 will increase, and if PaCO2 increases, then using this equation, the alveolar partial pressure of oxygen is going to decrease. As a result, partial pressure of oxygen in artery is going to decrease, which means hypoxia, and this is going to drive hyperventilation. So this entire mechanism can be explained by using the alveolar gas equation. So there is this interesting shortcut which we can use in case of metabolic disorders. In case of metabolic disorders with appropriate compensation, the PaCO2 is approximately the same as the last two digits of pH after the decimal points. So what does this mean? For example, let's take this example of this blood gas. In this blood gas, the pH is 7.26. The bicarb is 12 and PaCO2 is 25. So first, let's see what kind of disorder is this. Is this metabolic or is this respiratory? Because the pH is 7.26, which means there is acidemia. Now let's see whether this acidemia is because of bicarb or because of carbon dioxide. Now the carbon dioxide is on the lower side, but the PaCO2 is not high, which means that this is metabolic acidosis. And what we are saying is, in case of metabolic acidosis, the pH is 7.26 and the PaCO2 is 25. So 25 is really near 26, which means I would say that this particular case, the metabolic acidosis is properly compensated. Now let's verify that using the Winter's formula, right? So in case of metabolic acidosis, we use Winter's formula. When we use the calculation of Winter's formula, it turns out that for appropriate compensation to be present, the PaCO2 should lie in the range of 24 to 28, and in this case PaCO2 is 25, which means the measured PaCO2 lies in the predicted range, which means compensation. And we were able to say that this is a properly compensated metabolic acidosis even without using this formula, just by using the last two digits of pH after the decimal point. These are the references, and thank you so much. Please leave your questions and feedback in the comment section below.